Hello and a very warm welcome to Azure Thames Valley Meetup. My name is Alicia Dillon. I'm the Community Marketing Executive at SquaredUp, and along with Chris and Josip, one of the organizers for Azure Thames Valley Meetup. We just want to take a moment here to highlight our code of conduct. Our aim is to foster a community that is open to all and strives to be friendly and patient, welcome, considerate, and respectful. If you're willing to present something to the community, or if you happen to know a good speaker who might be, then please submit your session proposal via our Sessionize page. I will share the link to that page in the Teams chat shortly. We also want to continue to grow our community, so if you know of any Thames Valley locals who would be interested in joining our group, then please share our website and social media details with them. Again, I will share all of those details in the Teams chat shortly. And then finally, if you know any local businesses who may want to support us, then please point them in our direction. We'd love to chat with them. I'm now going to hand over to Josip, who will take us through the agenda for this evening. Over to you, Josip.
Thank you, Alicia. So this evening, obviously, the agenda is introduction and welcome, which we've just done. Alicia's just done for us. So tonight's presentation is Azure CosmosDB as a knowledge graph in SquaredUp cloud product. That presentation is going to be delivered by Richard Jones as CTO, our very own CTO, Chief Technology Officer at SquaredUp. Richard has got a wealth of experience in industry, starting from Symantec, Veritas, and Zona, and it's a mastermind behind our cloud product, graph knowledge graph database. Once the presentation is over, we'll have a question and answers. If you got any questions regarding the knowledge base or the actual Cosmos DB or SquaredUp product, the Richard and myself will be very happy to answer those. And finally, the last half now is reserved for networking and wrap up all the attendees. Hand it over to you, Richard, now.
Thanks, Josip. So hi, everyone. So yeah, as Josip said, my name is Rich Jones, CTO of SquaredUp. So I've been at SquaredUp now for 2 years, joined late 2019. And the last year of that time, I've been looking at sort of graph databases, and in particular, Azure CosmosDB, which is what tonight's session is about, focused on how we use CosmosDB within the SquaredUp SaaS product, which is a new product, as our knowledge graph. So I guess a good place to start is, why do we need a graph database at all? Well, SquaredUp's history is centered around Microsoft System Center Operations Manager, or SCOM. So we've got a mature product, 10 years in the making, which is kind of a market leader in providing data visualization dashboards on top of the SCOM object model. So it basically helps our customers make sense of the data they have in SCOM. But in this case, all the monitoring, the alerts and the notifications on those alerts, as well as the kind of the health state and the health roll-up, is all done by SCOM. So the most important bit there is that SCOM object model, which knows about the relationships between the various objects. And so what we wanted to do is take our experience from those 10 years and use it to create an enterprise observability portal, which isn't just for SCOM, obviously, because the world has evolved and it's still evolving. So everyone now probably has at least one public cloud in what they use. So they'll be using Azure Monitor or AWS CloudWatch or GCP monitoring. They're probably going to be using other tools like APM tools like Dynatrace, New Relic, Datadog or AppDynamics, as well as tools that support their applications and business services. So they might be using Azure DevOps or Circle CI for deploying applications, PagerDuty or ServiceNow for recording incidents about their applications. And so what we realized is that in order for SquaredUp to become this observability portal and be kind of a super aggregator across all of your platforms and tools, we would need our own unified object model provided by SquaredUp, where we actually connect the entities from your different platforms and tools. So just to give, by way of an example, imagine you've got an application running which has got a number of hosts in Azure. and those hosts might be then monitored by another tool, might be monitored by New Relic. There might be some synthetic monitors looking at them. They might be deployed by Azure DevOps, and so on. And so we want to be able to, in order to be able to provide answers to your questions about data, we need that unified object model so that we know where all the data relating to an application or business service is, so that we can pull that data on demand to provide data analytics, provide the monitoring ourselves across the top of all those different platforms and tools, and then we can do alerting on that monitoring and provide the notifications. And so the health state now will be sort of done by SquaredUp, and so we need to know the relationships between those different entities and the different systems, so that we know what depends on what, so we can then roll up the health state to the top level set of applications or business services. And so we think that a graph database would be a perfect fit for this, because it's focused on the relationships or associations between objects, and so that's why we started exploring with a graph database. So that's kind of why we needed a graph database. I guess the next obvious question is why CosmosDB? Well, I could probably answer this in one word, really, and it's we wanted something serverless. So the new SquaredUp SaaS product is 100% serverless technology. There's not a VM in sight, not a container in sight, and we wanted to kind of keep it that way. We also wanted consumption-based billing. So if I looked at when I looked at the alternatives, so I wanted to have something running in one of the main 3 public cloud offerings. So started off looking at AWS Neptune, but immediately you've got to create a cluster. You have to add instances to the cluster. You've got to size those instances, decide how many of them you need, and it's billed for every instance running per hour. You'll build for it. So even if you're not querying your graph, you'll still build for it. So I played around for that for a couple of days, got a bill for about $200, and thought enough of that. That's not what I'm after. Just want to pay for what I'm using. The only kind of other graph database that was in the big three public clouds is one from Neo4j called AuraDB, which is a kind of fully managed graph database. But again, just like AWS Neptune, you're asked straight away, what CPU size do you want? How much memory do you want to allocate to your nodes? And again, you'll build for every hour that those nodes are running. So again, wasn't what we wanted. We also wanted something that was kind of well established and been around a while. And so CosmosDB kind of ticked all these boxes. It was consumption-based billing. You just start storing data in your graph, querying it, and you're charged for just what you use in request units. It was actually GA'd in 2017, so it's already been around for kind of in market for 4 years. But it was actually founded right back in 2010. So there was a proto-Cosmos product that existed prior to Cosmos called DocumentDB. And that eventually became CosmosDB, and that's been around since kind of 2010. So it was pretty mature really, and as I say, fully serverless option. And so we quickly got up and going with CosmosDB. So I've kind of talked about why we needed a graph and why we started with CosmosDB. So I guess it's time to talk about, well, what actually is CosmosDB? Well, CosmosDB is a distributed multi-model database. And it's got these 4 different data models or APIs that you see in the diagram here. So I mentioned that it all began with DocumentDB back in around 2010. And so that's why you've got the document data model, and you query that using a SQL API, which is actually the DocumentDB dialect of SQL. So it's not quite pure SQL. You can reference JSON property paths in it. And by this time, MongoDB was the kind of main document database out there that everyone was using. And so the Cosmos team made it compatible with the MongoDB API for obvious reasons. And it was a similar story with one of the other data models as well, the columnar data model. Cassandra, again, was the main column family database out there at this time. And so it made perfect sense to make it compatible with that Cassandra API if you wanted to model your data as column families. They also absorbed into it Azure table storage as simple key value store. And then the 4th one, which is the one that we obviously make use of, and the one that's really important to us, which is the graph data model, which is an implementation of the open source Apache Tinkerpop, which is a graph computing framework. And the graph traversal language of that framework is known as Gremlin, and that's how you query your graph. And I'll give an example of of how you query the graph using Gremlin a little bit later on. So that's what Cosmos is. It's also worth pointing out that there's kind of there's probably many types of graph database, but there's two main types. There's the one that's really popular in academia, which has been around since about 1996 when the first spec was published, and that's called an RDF triple store. RDF stands for Resource Description Framework. Everything's described in terms of URIs. And really that's a subject, the reason it's called a triple store is you store a triple, which is a subject, predicate, object. So it's as simple as like Rich loves Marmite, Rich being the subject, the predicate being loves, and Marmite being the object. And so there's no kind of additional properties beyond those, beyond those triple things, the subject, the predicate, and the object. And then shortly after RDF became popular, I don't actually know for sure what the first labeled property graph was, but I know that Neo4j, which is probably the most popular one today, that started around the year 2000, so about 4 years after the RDF spec was published. And so RDF is really popular in academia, whereas everywhere in the commercial world, everyone uses a property graph. So if we look at kind of what a property graph is, so within the graph itself, it's made up of vertices and edges. The vertices you see there are the people in blue and the houses or studios and apartments in orange. And you can see that as well as you've still kind of got the subject predicate object in the label of the vertex and the edge. So you can see that person student 1 lives in house apartment 1. But in addition to that, you can have an arbitrary number of properties with each vertex and edge. You can see that the person student 1, their name is Charles E, they're born in 1987, and you can have any number of properties you want associated with that vertex. Similar with house apartment 1, you can have an address, a surface area, number of rooms. And so you can have any number of properties associated with the vertices, and even the edges themselves. That lives in edge, which you'll notice is directional. The person lives in the house, and the direction is very important. And you can see that you can have properties associated with the edge as well. So you can see that they began living there in 2012 and finished living there in 2013. And those edge properties, they're not associated with the person or the house. Those properties are of the association between the person and the house when the person was actually living in the house. So that's what a property graph looks like. So it's vertices and edges with an arbitrary number of properties per vertex and edge. So then you might be wondering, okay, so that's a kind of general property graph. What does the kind of knowledge graph that we use in SquaredUp SaaS product look like? What sort of data are we storing in there? What sort of vertices and what sort of edges? So I give an example of that. So I've chosen here that we've got a sales application, which is running in Azure, Microsoft Azure. You can see that it's being monitored by a outside-in availability monitor in Pingdom. So you can see that the vertex that is the monitor monitors the vertex that is the application, and you can see the direction to that edge relationship. It's deployed by an Azure DevOps pipeline that deploys the application, and it's hosted on a host called Apo1. Now, all of that kind of is pretty obvious, I guess, and makes sense. The relationships are pretty obvious. What the vertexes are and what they represent is pretty obvious. But there's this bit at the bottom here is a little bit more complicated. You can see these is relationships between a host called Apo1 in Azure with a host called Apo1 in New Relic, and this canonical host also called Apo1 in the middle there. And what this is where we have the same entity that we detect in different systems. So in this case, we detected this host in Azure, and it's also shown up in New Relic because New Relic is monitoring it. Then what we do is we create one of these canonical nodes. And you can think of this like inheritance. So just like a car is a vehicle, well, these source-specific hosts, the one in Azure and the one in New Relic, is of type, this canonical host type in the middle there. And then you've got this directional edge between them. So they are, because they inherit from it, if you like, then the is relationship is pointing towards that canonical node. So you can think of it as the base class, if you like, and it's the common properties across all of the nodes that relate, that are the same entity. So if I dig into that a little bit more, they're what we call equivalence is relationships. So it's to show equivalence between two things. When we first started thinking, how are we going to store this data? How are we going to model it in our graph? The obvious thing was, oh, well, they are the same, right? So the host in system X is the same as the host in system Y. And equivalently, the host in system Y is the same as the host in system X. They've got the same fully qualified domain name. They are the same host. And that would require kind of these two-way relationships because there's no kind of direction to it. One's the same as the other and the other one's the same as that one. And you can see there's quite a lot of edges here. And if you imagine now we also saw that host in system W, then we'd need two-way relationships between W and X, W and Y, and W and Z. And you can see that would get very complicated very quickly, and there'd be a lot of edges to maintain. So rather than doing that, we decided instead to create these canonical nodes, which is kind of the common properties across those three different systems. And then the relationships become a lot more simpler. They're one-way relationships because they inherit from that canonical. So the system-specific types are of that canonical node. And so now it's a lot simpler, a lot less edges. And if another one came along in system W, then all we literally need to do is create a single edge from that system W host to the canonical host that it is its common properties or its base class. So it's a lot more simple. So this is how we kind of model these equivalence relationships. So this is a kind of really important part of our product because it's how we correlate the same entity across different platforms and tools. So I thought at this point it'd be worth kind of a quick show and tell in our actual SquaredUp SaaS application of how the graph database manifests itself. So I'm going to show you our order processing sales application. This is an application that's used by our sales team to demo to prospects and customers. So it's a real application, but it's not kind of it's not the SquaredUp application. It's one that we've kind of created for demo purposes. So I'll just switch across to SquaredUp application. And so this is just kind of a top level dashboard that I've created. You can see that it's called SquaredUp Pulse Check, and it's showing all of our different business services, and it's just showing the health of those business services. So a couple of them don't have any health, the ones that aren't shown in the color. And then we have these various business services that have sort of state associated with them. You'll notice when I hover over them, it says workspace. And so these kind of top level entities, we didn't know whether to call them, are they teams? Do we want to create one of these workspaces for each team, like your DevOps team, your operations team? Do you want to create one per application, one per business service, one per microservice? And we decided, okay, let's just abstract that away. Let's just call them workspaces. And you can make that whatever you want. So, different customers will model it in different ways. A workspace basically is a container for a collection of dashboards and other things. And so you'll kind of create them how you see fit, whatever fits with the way that you've got things organized in your organization. And you can also then create dependencies or relationships between those workspaces. So I've got a very simple one here where the SquaredUp business services all roll up to this parent SquaredUp organization workspace. And you can see there the health is rolling up as well. So because the order processing application, which I'm going to show you in a minute, has gone down, it's gone red, it's got something wrong with it, then that rolls up to the top level SquaredUp workspace. So I can see at a glance on this SquaredUp Pulse Check, I can see that there's a problem within the SquaredUp organization, and that problem is with the order processing application. But these relationships of workspaces can be as complicated as you want. You can have then these business services that can then each have a set of technical services. Those technical services can each have a set of microservices within them, and so on and so forth. It's probably worth also pointing out that even though this wasn't intended when we first started with the product, these are also entities within our graph database. So we decided, well, we need to have relationships between these workspaces. Well, we had a graph database, which its purpose is to model relationships and associations. We thought, well, why not put the workspaces and the dashboards into the graph so that we can then, that's how these relationships are maintained, as edges in our graph. So that kind of came about a little bit by accident, but I can sort of show you that just briefly if I just copy a little bit of that, the name of that dashboard. Because everything in our graph is indexed, I can quickly search and I can find that dashboard, I can see the name of it, and I can see that the workspace called SquaredUp contains this dashboard that I'm looking at now because I'm currently within the SquaredUp workspace, this top level workspace. But that kind of came about, we didn't sort of plan it that way initially. Our initial plan was to, represent, as I say, the entities that make up a business service or an application, which I'll show you now. So if I click on that order process and application, I'm just going to change the time frame to 7 days. So you can see here, the first thing you see is an application map for that order process and application. And you can see here this graph view straight away where we've mapped everything out. And if I hover over the middle there, you can see that is the application entity. This application is an application which is hosted in Azure. So there's a number of hosts which you see up here. So we've got a host called Web02. We've got another one down here, Web01, and that's probably Web03. So it's hosted on these 3 hosts, which are running in Azure. It's monitored in New Relic. So we've got a number of monitors here in New Relic that are monitoring the application. You can also see down here, we've got a SquaredUp ServiceNow organization that application belongs to. And that's because we record incidents for this application in ServiceNow. It's enabled by .NET Technology Stack. It's deemed high criticality because it's used by our sales team to demo every day. And it's owned by Ash in our solutions team. So kind of everything about that application you can now see. And the reason we do that is because this is how we turn it into kind of a knowledge graph where we know where all the data relating to this application lives. We know some of it's in New Relic, some of it's in Azure, some of it's ServiceNow, so that we can then on demand fetch data about it to build these beautiful dashboards that you see, showing you everything you want to know about your application. So you can see here, we're showing the throughput for that application coming straight out of New Relic because we know that we can run an NRQL query against New Relic because we know that the application is being monitored there. Because we know the hosts are running in Azure, we can go and query Azure for the host CPU percentage. Because we know the incidents are recorded in ServiceNow, we can go and retrieve those incidents on demand. We can get the AppDex score from New Relic. And importantly up here, we can get the state of the monitors that are monitoring the application. And you can see because one of them's gone red, we can actually turn on monitoring on every individual tile. So I could turn on monitoring for any one of these tiles based on the data that's shown within that tile. So based on the throughput of the application, I could make it go, red, amber, or green based on the CPU percentage of the hosts. So the only monitor I've turned on for this application is I only care about kind of the outside-in availability. So you can see that because one of them's gone red, the tile health has now gone red. It's in the error state. And you can see that tile health, that tile health is then rolled up to the dashboard health here. And that is in turn rolled up to the order process and application, the workspace. And as you saw, that rolled up to the top level SquaredUp workspace. So all that health rolls up. And as I say, we can start monitor based on the data in any tile that you're interested in monitoring and that you want to get the health state for. And that will roll up across the entities. Those dependencies, again, are modeled in our graph database. Now in here, though, you'll notice that you don't see any of those is relationships that I talked about. And that's because you're not interested in them. You just want to see the application as one entity. You want to see the hosts as one thing. But if I show you quickly that they are actually there under the covers, if I edit this dashboard and do a little bit of tweaking in the editor's going to load. So by default we collapse these what we call canonical nodes. If I switch that over and save this, you can see that this has now changed this diagram. You can now see, well, actually there's 2 applications, and that's because there's one that New Relic knows about, and there's one that ServiceNow knows about. It's recorded as a configuration item or an asset in ServiceNow. And we can see that those applications are in fact the same application. They have this equivalence is relationship between them. And the same for the hosts up here. The host is known in New Relic because New Relic is monitoring the host, but the host is also running in Azure. So we know about that host there, and we've correlated those. We know that they are the equivalent host. They are the equivalent entity. So we collapse all that down. So we give you, that single view of every entity, because you don't really care where it's running. You just want to see data on demand from all of those places, so you can then see the data in your dashboards and also turn on monitoring of that data and roll up that monitor health. So if I now just switch back to my slides. Excuse me while I find those. Okay, so that was kind of a quick show and tell of, hopefully you now got a good understanding of kind of how we're using the graph database within our product and how it provides a really important kind of health state roll up across dependencies and how it pulls in everything related to a application or business service so that we know where all the data relating to it exists, so we can query it on demand to do in-place analytics and health state, get health state and roll up that health. So that's kind of how we're using it. Well, how do you, if you wanted to get started with CosmosDB, how do you go about doing that, really quickly? Now, obviously, if you were deploying this for real, you would use your infrastructure as code software tool of choice, Terraform or whatever it is you're using, to go and deploy the resources, deploy the Azure CosmosDB database to Azure. But if you want to get going really quick, just go into the Azure portal, click on Azure CosmosDB, press the create button. You'll be asked a number of questions when you create the account. First thing you'll be asked is, when all data is encrypted, so do you want to use a service key which is shared across all of the tenants, or do you want to create a customer managed key where you can have a different key for each customer? You're also asked about the availability. So I mentioned earlier on that it's a distributed database. So the data is distributed across different zones or regions, and you can choose whether you just do it across different availability zones or whether you want to actually distribute that data across different regions. The data is all backed up, and you just choose how often it's backed up. So at what specific interval it's backed up, and how long you keep those backups for. Do you want to keep them for a week, a day, and so on? And same with the backups, what sort of redundancy level do you want? Do you just want local redundancy, or do you want your backups to be replicated to different zones or to different geo-regions? And then the last thing you're asked is kind of a bit of a puzzling one at first, but an important one, which I'll go into a bit more detail on, is do you want provisioned or serverless capacity mode? And so you're thinking, well, I'm not quite sure. The first one I went through, well, I'm not quite sure what is the difference. The difference is fairly important. So in provisioned mode, you're sort of provisioning up front a certain number of request units per second, which is what your build based on. You'll build based on the number of request units per hour. So there's no kind of instance size or number of instances. It's just the amount of traffic you get, the number of request units you use up. And so if you knew what your pattern was and you wanted to guarantee, a certain sustained performance for your traffic, then you could say, okay, I want exactly 10,000 request units at all times, because you know exactly what your usage patterns are. Now, when you first start using Azure CosmosDB and a new product, you're not going to have a clue what your traffic patterns look like, and so you're going to be thinking, well, I don't want to pay for more than I need, and so how do I avoid that? And there's kind of two ways of avoiding it. One way is that you turn on what's called auto scale with that provisioned capacity mode. And so with auto scale, you configure the maximum request units, so the most you're ever going to get charged. So imagine you configure the maximum to be 10,000, then it will automatically scale between 10% of that maximum. So in that case, 1,000 and that maximum. But the only thing is, it's only got 1 hour granularity. So if you look at this picture in the bottom right here with auto scale provision throughput, you'll see that it's scaling from the minimum, which is 10% of the maximum, up to the maximum. But every time it scales, it'll stay there for 1 hour of granularity before it drops back down. So it does mean that you're always paying for 10%, and you're always paying for it as it scales. You're paying for it for a minimum of 1 hour, and it'll only come back down if the amount of traffic you're seeing drops back down. So it's not ideal, but there is a free tier as well. So if you provisioned 10,000 request units, then the minimum obviously is that's running all the time is 1,000, and the free tier is actually 1,000. So you get the first 1,000 request units for free. So that's a good kind of starting point, is to go with that 10,000, because then when it's at the minimum, which is probably most of the time, you're not actually paying for it. But there's also a model which is called serverless, a different capacity mode. And that is obviously there's no provisioning of any request units. You pay only for what you use. So when you're first getting going, like we were, haven't got a clue how much request units you need, then it's perfect, because you're charged only for what you use. And with serverless, there's kind of no minimum, and there's no kind of minimum duration of 1 hour. So the serverless graph looks like this one here that I'm highlighting. And so you get the spikes, and you're literally paying for the kind of millisecond of those spikes just when they occur. And there's no minimum. So if there's nothing going on, 0 request units going on, then you'll charge 0. So serverless sounds absolutely perfect. And it would be if it wasn't for 2 constraints that CosmosDB currently has with serverless. One of them is that the current maximum request units of serverless is 5,000, and 5,000 isn't actually that much. So it was great for getting going, but once we started having lots of tenants using it, then we soon hit that 5,000 limit, and we needed higher. The other limitation is that the graph container size itself with serverless is limited currently to 50 gigabytes. Which for what the data we store, we're not storing much in the graph. It's just like an index of all your entities. And we store about a dozen properties for each vertex and about 3 or 4 properties for each edge. So for us, it was, that wasn't a factor. 50 gigabytes is plenty big enough. But that 5,000 was a bit of a limiting factor. So I did talk to the Cosmos team, and they have said that they are going to be removing those limits. It's kind of nuts in a way. Why would you have a limit on serverless? I want you to charge me for what I use. If I use 500,000, charge me for that. That's the whole point of serverless. So it is strange that they put that limit in place, but they've assured me that in early 2022, the serverless limits will be removed, and so there will be no container size maximum, and there'll be no request units. So we started off with serverless, and then because of that limit, we did move across to the provision with autoscale, where we're autoscaling up to 10,000 currently, but we do plan on going back to serverless as soon as these limits have been removed. Before you can query your graph, which is obviously really important, the whole point of having your graph database, it would be a bit stupid just to use it as a persistent store where you want to just retrieve data. The whole point is that you're querying a graph and you're traversing your graph. Before you can do that, you need to index the properties of your vertices and properties of your edges. Now, the default indexing policy when you set up your CosmosDB account, and this is what we went with, we had no reason to change, is every single property of every item, and by item I mean vertex and edge, every property is indexed. And so with strings and numbers, you also have range indexes. So you can do like between operators, for example. So a property is between 5 and 500. And yeah, we went with this just because we only index about a dozen properties, so it wasn't going to cost us that much more. And also, we want to query on every single property, and we want to give our customers the ability to search on every single property in the graph. But if you do have a different use case where you want to have some properties that are retrievable but not searchable, then you would set up an indexing policy, and that's basically a whitelist or blacklist. So you can specify include and exclude paths, and they're specified by the JSON property path of the property you want to include or exclude. The other way of controlling it is via the indexing mode. So there's 3 different indexing modes. You can turn indexing off altogether, which is none or disabled. You can index in an asynchronous lazy fashion, where when you're updating your graph and you make a write, well, the index isn't consistent straight away. It's eventually consistent, so you might have to wait a while before your searches reflect the latest data. Or the mode that we use, which is the default consistent mode, which is synchronous. So as the graph is updated with your writes, then the index is immediately updated as well. And that's makes your application a lot simpler, because there are certain use cases where we do actually query for data pretty immediately after we've written it. And so rather than have to work around those, we went with the default of consistent indexing, which means you can immediately search on anything that's been written to the graph. And then in terms of the cost of indexing, well, I've already mentioned that you're charged based on your usage, so the request units that you use when you perform graph operations such as queries. But on top of that, you're also charged for the storage that your graph consumes, and that total storage that you'll build on is the data size plus the index size. That's the total size that you're consuming and what you build on. Now, with a lot of different NoSQL databases, you've got to kind of do index compaction, and you've got to take care of it yourself. You've got to do these kind of background operations that run every day or so. You don't have to do that with CosmosDB. When data is deleted, then the indexes are automatically compacted for you. So there's nothing you need to do, which is very convenient. So that's kind of the important bit about setting up indexing and being able to index all your properties for the whole purpose of being able to query the graph. And so you query the graph using the Gremlin language, which as I mentioned earlier, is the graph traversal language of the Apache Tinkerpop graph computing framework. It's pretty powerful, but it is fairly complicated to get going with. So I thought I'll best demonstrate it with an example, which I'll do in the Azure portal, actually. So you can actually query a graph right in the Azure portal. But before I do that, it's much better for me to show you the data we're going to be querying within our application, because the visualization isn't that great in the Azure portal. It's much better actually with our application. So I'll show you the data that we're going to be querying, and then I'll switch over to the Azure portal to show you the queries. So I'm going to pause, take a quick drink. Okay. So I'll switch back to our application. And you'll see up here, I have a Star Wars workspace. So we can actually put any data we want into our graph. We have APIs for absolutely everything. So anything that can be kind of represented with with vertexes and edges, with relationships between those entities, you can put into our graph using our APIs. So I thought it'd be interesting to kind of put the Star Wars data in there. So I don't know if you're familiar with Star Wars API, which is swapi.dev, if my memory serves me correctly. And so this is just querying those Star Wars APIs to get different entities and putting them into our graph. So this is a subset of the graph. This is showing Star Wars vehicles and starships, and then it's showing a relationship between them, who pilots them, what film they're in, and so on. So you can see, if I look at this film here, this is The Empire Strikes Back. You can see that it contains the ATST Star Wars vehicle. It also contains the Slave One starship that is piloted by Boba Fett. You can see that you've got another pilot here, Chewbacca, who pilots multiple vehicles. It's got the Imperial Shuttle starship, the Millennium Falcon, which is also piloted by Lando, I can't pronounce that, Calrissian, whoever that is. I'm not a Star Wars fan, as you might be able to tell. I do know who Chewbacca is just about, but that's about it. And then you got those starships are contained within New Hope. So you can probably get the picture here. It's kind of relationships between the films, the vehicles shown in those films, the pilot of those vehicles. So I'm going to go and query this graph, or this subgraph, this part of our graph, using the Gremlin query language. So I'm going to go and get kind of a query like the list of the starships and vehicles, the names of them, grouped by the pilot that flies them. So that's actually sounds quite simple. You know, in SQL, you can imagine a group by pilot somewhere at the end. In Gremlin, it's a bit more complicated to build that up. We've got to traverse the graph, first of all. So I'm going to just switch to the Azure portal to do that and explain how you use Gremlin. So in terms of running Gremlin, probably the most simplest query you could run is something like this, which is g.v.count. I'll just run that. And what this does is queries the graph for number of vertices. So G at the beginning there just means graph. .v means the vertices of the graph. So please query the vertices of the graph. And .count, give me a count of the vertices in the graph. So pretty straightforward. There's just short of 40,000 vertices in this graph. I can do a similar thing with the edges. If I wanted to query for edges, it's g.e, so graph.edges, and I can get a count of those. But it's usually more interesting to query vertices in the graph. So now if I get rid of the count, if I did that, that would go and return those 38,900 odd vertices if I ran that. I don't want to do that because that's going to take a long time and it's going to probably blow up the user interface here. So instead, I'm going to kind of filter the graph, and you do that using something called has. So I'm going to do .has, and then you filter it based on the property of the vertex. So I'm querying vertexes here, g.v vertices, and I'm going to query it based on a property called source type. I'll explain why in a minute. And I'm going to query for the value of that to be Star Wars person. So I'm going to run that query. If I've got that right, I will get back, I'll get back all of the Star Wars people that are in the graph. Now, this property source type, what's that? So if I quickly go back to our application, if I click on one of the entities here, so we can drill down into any one of these vertices. I click on Chewbacca, and then we can see that as well as getting a kind of topology view of everything, graph view related of everything to do with Chewbacca, so the planet he resides on, his species that classifies him, all the films that he was in, all the vehicles or starships that he pilots, and you can see those pilots edges that I'm going to query any minute. You can also see we've got a details pane here for showing the actual properties in the graph. So these are the properties, each property of that vertex in our graph. And as you can see that we've got a property called source type, and it's of type Star Wars person. So all of the people in the Star Wars data set have that source type property Star Wars.people. We'll have different, for the vehicles, it'll be source type is Star Wars.vehicle or Star Wars.spaceship and so on. So that's what I've queried here. So I've basically queried for, if I go back to the Azure portal, I've queried for all of the different Star Wars people. So this is showing me the results down the left here, all the different Star Wars people. And in the middle here, it's just showing you the one I've selected. So I've got selected Luke Skywalker, so he's in the middle. And you can see that all of all it shows you in here is his immediate connections. And that's why I said it's not as good as what you see in our product. You can see the whole graph and all the different relationships. All I can see here is the immediate relationships. And it also doesn't show you the edge labels, which are really annoying. To see the edge labels, you kind of got to scroll down over here and see, okay, I can see that he pilots a snow speeder. He resides on Tatooine, however you say that, contained in those films. But the visualization, as you can see, isn't as good. But that's the Star Wars people. But I mentioned I wanted to query for the vehicles and starships that are piloted by the people. So to do that, I've got to start traversing the graph. So you'll have seen that there's the edges from the Star Wars people to the starships and vehicles. They had a pilot's edge. The person pilots the vehicle, and it's in that direction, right? So it's coming from the person to the starship. So to do that, that's called an outward edge in Gremlin. So it's called an outward edge because it's going from the vertexes I have in my current iteration, the people. It's going out of the person into the vehicle or starship. So to query that, to traverse along that edge, in other words, to go to the vertex or vertices, I should say, at the end of those edges, you do .out. Now, if I just did .out like that and didn't specify anything else, that would go to all of the edges at the end of any Star Wars.person. So I've now not just got the vehicles and starships, I've also got anything at the end of an outward edge, including like the planet they reside on. But I'm not interested in that. I'm only interested in the vehicles and starships that they pilot. So I need an edge label in here, so pilots, if I can spell. So I put pilots in there. So that will now traverse the outward edges from the people, and it's only going to traverse the pilots' edges. So I traverse those edges, and I can now see that Luke Skywalker pilots a snow speeder. In fact, what I've got down here now is just the Star Wars vehicles and starships. And because I've got snow speeder selected, it will show the immediate relationships to that what is that, a Star Wars vehicle, and Luke Skywalker is the pilot of that vehicle, so you can see that. And so I've now got the list of the vehicles. But if I go to the raw graph output from that query, you can see it returns JSON results, and you can see that it's a vertex. It's an array of vertices, as you might expect, and every vertex has a bunch of properties, including that source type property that I mentioned. But I'm not interested in all these properties. I just want to know the names of those vehicles. So I can, at the end of here now, I can say, okay, I'm only interested in the values of the name property. And so if I query that, I now just get the names of those vehicles and starships. You can see I'm getting duplicates. I'm getting snow speeder here and up here, for example. The reason I'm getting duplicates is because that vehicle is piloted by more than one person. If I was only interested in just the unique or deduplicated set of them, I could put dedupe query on the end there. And I now get the deduplicated set of, that's the full set of vehicles and starships piloted by any Star Wars person in the graph, because I started with all the people and then I went along the outward edge to get to these vehicles and starships. But I don't need the dedupe in what I'm going to do. So I mentioned at the beginning, I'm going to query for this list of vehicles and starships, but grouped by the person that pilots them. So a little bit like SQL, to do that, I've got to do a group by. So I do a group dot by, but I now want to group by the pilot, by the person. Now, that's tricky because I started on the people at the beginning, right at the start of my query. I had the people, but now I've gone off those people. I've traversed along those edges to get onto the vehicles and starships. But fortunately, rather than have to re-query for it, Gremlin allows you to remember any point in your traversal. So I can do as, and I can give it any name I want. I could call it anything, and I call it something sensible like people. That doesn't impact the traversal in any way at all. It just means that when you get to this point in a traversal, in other words, so just the bit just before the .as, now go and remember that set of vertices as people. I've given it a name before you then go and start traversing the edges to get to the vehicles and starships. So I now have remembered the people part of the query. So I can now select. I've remembered that part of it and given it a name, and I can reselect it at any point later on in my query. So I can now do select people. So I want to group the vehicles and starships by the name of the person. So I can select people from earlier on in my traversal. And I want to do it by the name of the person. So if I've got this right and not missed any brackets or closing quotes, that should give me, the names of the vehicles and starships grouped by the person that pilots them, which is what I was after at the beginning. So as you can see, Gremlin it takes a bit of getting used to. At the beginning, at the start, the queries are quite simple. If you just want to query the vertices based on a property or set of properties, and you just keep doing. If you want to query on filter on multiple properties, you just do has, and you just do as many has clauses as you want to filter on more and more properties, and they by default are ANDed together. If you want to do an or, you can do a .or, and then have multiple has queries within that to do a or. This property is this, or this property has that value. So I'm just kind of trying to give a flavour of Gremlin today, obviously, because we're very limited on time. But if I switch back to my slides, learning Gremlin was difficult. It's every reference out there, so you normally rely on your Google foo to find references and you just read up on it. I was kind of getting nowhere fast. It was all really complicated Gremlin queries that I didn't understand, and I couldn't really find anything that built it up very gradually. But eventually I did come across what I now call the kind of Gremlin Bible, which is this. It's free to download. It's available in PDF or HTML format, and it's called Practical Gremlin by Kelvin Lawrence. And this kind of is quite big, so it's 455 pages, but it builds it up really gradually from a really gentle introduction to how you query the graph, how do you query the vertices, edges, and then goes into loads and loads of detail way beyond my current knowledge. I think I've got to about page 100 out of 455, so I've got a long way to go, but you kind of just use it to look up things as you need to. It's a great reference to go back to whenever you need to look up how to do things. That's given you a sort of flavour of Gremlin. So I just want to kind of summarise that what I've kind of shown you today is so why we needed the graph database, why we went with Azure CosmosDB, and then how we use that within the new SquaredUp SaaS product, and how we use it as our knowledge graph to relate different entities from all of your platforms and tools together. So we index all those entities using our graph. So anything in our graph is searchable. So customers can search for any entity from any of their platforms and tools to then on demand pull data from that into tiles for visualization and for analytics. And then you can set up monitoring on those tiles, which can then be rolled up through the different workspaces to the top level business services, right up to the top. And then you can enable alerts and notifications on that. So it's kind of a summary of what I've shown today, how to get going with it, how to index properties, and how to query the graph, which is a really important part of it. So with that, I will open it up to see if anyone has any questions about anything I've sort of shown or talked about. Doesn't look like there are any questions.
Richard, I've got one question. So when you've been talking about the correlating nodes and then creating canonical nodes, so with the is relationship, do you always use name and source type or type properties to derive that correlation, or you could, or actually, which properties do you use?
Yeah, that is a very good question. If I just switch back to our application. So yeah, there's kind of two ways actually that happens. Some of them are what we call like built-in correlations. So imagine a host is a good example. So you've got quite a strong property, which is the host, a fully qualified host name. If that fully qualified host name is the same, and because it's fully qualified, it should be unique within your kind of environment. And so we can automatically then correlate that based on the fully qualified host name. We do similar things for things like databases, where if it's the same host for the database and the same database name, then we can pretty safely assume that is the same database. It's running on the same host, it has the same name. But in addition to that, what we realized is, it'd be quite, we don't understand the data as well as the customer is going to understand their environment. They're always going to know more than we do about their environment. And so we allow you to set up what we call custom correlations. So as well as having these built-in ones for sort of strong types where we know all about that type like a host, we can also allow you to set up custom correlations, which are kind of rules where we correlate things. So good example here, and this is what was used actually to correlate the application, the New Relic application with the, which is in New Relic, with the order processing platform in New Relic with the order processing platform in ServiceNow. So the vertices both have an application ID. New Relic has that application ID, and when we created the asset in ServiceNow, the configuration item, we give it that same application ID. So you can see here, app to app by application ID. So you can see if you've got two different applications, they're a type app, and they have an equivalent application ID property. Then create an association between them, which is using this is relationship. So this equivalence relationship. So they're treated as the same. And you can do that for different, for anything. So for any types, any property, you can create these custom correlation rules. We'll probably enhance these in the future to base it on, multiple properties rather than just the one. But right now it's just the one. I've got another one here where you might want to correlate applications based on the name of the application. And I've got another one where I'm correlating a monitor to its application by ID. We do also have built-in correlation for monitors, where if we know the URL of what's being monitored by the monitor, then we know, or that URL is associated with that application, and we can automatically correlate the monitor with the application as well. Does that answer your question, Josip?
Absolutely. Thank you so much, Richard.
Brilliant. No worries. Any other questions from anyone?
I think we got one in chat. I think Malcolm asked, other than Star Wars, what applications suitable for use with Cosmos DB? I know Ben is typing probably something, but perhaps Richard, or you can help Malcolm with that. Or Malcolm, you can go online and then ask what you actually meant by that. Is there any specific use cases you would be looking for?
Hello, can you hear me?
Yes, we can, Malcolm.
Right. Now, I've not come across this before. This is completely new to me. It looks fascinating. I was very interested in this interrogation of the database using Gremlin. So I was just wondering what your other what people are actually using Cosmos DB for.
Yeah, it's a good question. So I was brand new to Cosmos DB a year ago. So I've only ever used it within the new SquaredUp SaaS application. I'd never used it before. So I don't actually know, because it's a multi-model database. I do know that most people use Cosmos DB as a JSON document store. So those 4 data models that I showed at the beginning, it's mostly used because it was originally document DB, which was the proto Cosmos product, and it became Cosmos. Most people are using that data model. I'm not sure how many people are using the graph data model and what sort of graph data they're using it for. Obviously, in our situation, it's kind of resources, infrastructure, entities, and different platforms and tools to correlate those, as you've seen in the various demos. The Star Wars one was just a bit of fun, obviously, to show a fairly straightforward Gremlin query.
So would I be correct in assuming that if you compare it to something like MySQL or something like that, that it's the actual index thing that allows you to connect these documents together that's the important part of the database?
Yeah, that's exactly right. So the every item, and by item I mean vertex or edge, the properties of the vertices and edges are indexed, which means, and including the labels themselves, that pilots label, which means that you can do the queries between vertices. So you can traverse the graph from vertex to vertex and query along those edges. And so you can see, what are the vehicles piloted by a person rather than just what are the vehicles or what are the people.
So what's the difference between the vertex and the edge? Because if you've got in Star Wars, you've got the spacecraft and you've got the pilot. What makes them a vertex or an edge?
Yeah, let me go back to the Star Wars data so I can kind of show it again. So the vertices are the circles that you see here. So all of the entities like the starships, the pilots, the films, they're all vertices. The edges are basically the arrows that you see. So
they're the connections.
The connections, the associations, relationships, connections, whatever you want to call them. And so the edges, just like when I gave that example right at the beginning, a person living in a house, and it was lives in was the edge. But you can have properties associated with the edge. So the example I gave earlier, when a person lives in a house, the start and end date of the association. So a property of the association will be stored on the edge. So as well as that edge label, that edge can have other properties which are related to the association between the person and the starship.
Okay, thank you.
Like the date they started flying it, the date they finished flying it would be an example there.
Right. Thank you.
No problem.
I was just going to add, Malcolm, the kind of canonical example of graph database usage is social networks like Facebook, because they frequently need to be able to, run queries like find me the friends of my friends, and those kind of questions are fairly hard in typical relational databases. But something like graph databases, like Richard has explained, queries like that become very quick and very easy.
Okay.
Yeah, so these traverses along the edges, you can repeat them, so you can and obviously you've got to be careful that you don't go round in circles, and there's ways to protect against that in Gremlin, that you don't just go on an infinite traversal around your graph, but you can do kind of these cyclic path queries where you're going along repeatedly across certain edges to different entities. So in the example Ben gave, like friends of friends of friends of friends, but or the LinkedIn's another perfect example of a graph database, where you connections, and you got connections of connections of connections, and you want to see connections. I think it shows you sometimes this is a third removed connection, it will show you, and things like that in LinkedIn. That sort of thing is, how many edges does it need to traverse before it gets to from person A to person B.
Okay.
Okay, well, thank you everyone. If you do want to know any more about the SquaredUp SaaS new SaaS product that I've shown you today, then please do go across to SquaredUp.io. So it's not on SquaredUp.com, which is our company website, because it's it's in the early days. You can request access now. It is available, and you can, if you're interested, you can fill in the form here and request access. There has been quite a lot of initial demand for the product, so we're onboarding customers in waves, but we will get back in contact, arrange a demo, and arrange for you to have access to the product if you're interested. But yeah, hopefully you've found out a lot about graph databases today, about how we're using it as a knowledge graph within our new SaaS product, and also seen just how beautiful our new SaaS product looks as well. So yeah, thank you very much, and
Thank you.
Thanks for listening.
Thank you, Richard. That was a great and insightful presentation, and great product, by the way, as well. I think I'm going to share my screen now again, if that's okay.
Yeah, I'll stop sharing. Oops.
No, it's fine. Thank you. Well, thanks everyone for attending, and thanks Richard for presenting on the Azure CosmosDB and how it's being used in the SquaredUp cloud product. So before we go to networking and the general chat, so just to let you know that this is a last meetup for this year. So hopefully everyone is going to have a nice and relaxing Christmas break. And then I only want to ask you to keep an eye on the meetup.com for Azure Thames Valley for exciting things to come in next year. And we still got some time to do socializing, networking, and then as it says on the slide, we always on the lookout for great speakers, which you can, if you got any ideas or desire to present, you can always submit your presentation to Azure Thames Valley speakers on the URL being shown here. So for the remaining time, if you've got Pai and Malcolm, if you got any questions, not necessarily related to the presentation, but in general about the meetup, we would love to hear.
Hello.
Hello.
I think I'm going to wish you a Merry Christmas and Happy New Year.
Thank you,
And
Malcolm.
I think I'll leave it here, and I'll look out for the meetings coming up in 2022. And hopefully it would be nice to sort of start meeting up in person again. But we'll
Yes,
have to see how it
absolutely.
goes.
Absolutely, Malcolm. We shall see what's possible in the next year.
Yeah. Well, thanks for that. Very interesting. I'll do some research on CosmosDB, and I look forward to seeing you next year.
Thank you, Malcolm.
Thank
Have
you,
a nice
Malcolm.
cheers.
Cheerio
Bye-bye.
then.
Bye-bye.
Bye.
Bye.